it's coming. It's kind of slow, but it's coming. Okay, so for the homework, let's start with here, homework number 4 solution. Okay, it is coming. Okay, hold on. The page that I wanted to present actually shut itself down, so let me try to restart the page. Okay, it is kind of slow, but it is coming. Okay, so here is the homework number 4. Is the following set a spanning set for R3? So here you have a set with vectors inside of that set. Now the question is this set that contains vectors considered a spanning set? Now a span is actually the set of all of the possible, like if you have some vectors and we say that these vectors are spans of a subspace, that means that that vector can be written as a linear vector, as a linear combination of any vectors inside of that that vector space. Now here the question is, you have this vector space R3. The question is this vector here a subspace? Is this vector okay, is this set a spanning set of R3, meaning that can we write these vectors as a linear combination of any vectors inside of R3? So to do so, let's go here. So here what we need to do, we take an arbitrary vector in R3. R3 is actually the set of all of the vectors with 3 components. Okay, so I randomly select one vector from R3, and now I take that vector such that A, B, and C belongs to the set of real numbers. Now in order for this set to be a spanning set, I need to be able to write it as a linear combination of any arbitrary vector of R3. So I select coefficients, let alpha 1, alpha 2, and alpha 3 and alpha 4 be real scalars. Now if S is a spanning set of R3, then we can u, the vector u that is here, which is a vector, an arbitrary vector from R3, that vector can be written as a linear combination of the vectors in the set S. In other words, I can write u equal to alpha 1 1 0 0 transpose plus alpha 2 1 0 0 transpose plus alpha 3 1 0 0 transpose plus alpha 4 1 1 2 transpose. So if I can find coefficients alpha 1, alpha 2, alpha 3, and alpha 4 such as this is true, then I can say that these vectors, this one, this one, this one, and that one, they span R3. So here I take the vector a, b, and c, that the vector u that I have. So u is actually is a, b, and c. Alpha 1 stays like this, alpha and then 1 0 0, the version of it as a column vector is this one. So and then I multiply alpha 1 here and I do the sum and I obtain this. Remember, my goal is to find alpha 1, alpha 2, alpha 3, and alpha 4. So I noticed this is like a system of equation with unknowns alpha 1, alpha 2, and alpha 3, and alpha 4. And when I solve it, and I obtain the following: alpha 1 equals to a plus b minus c, alpha 2 is equal to b, alpha 2 is equal to okay, where was I? Hold on. So I was saying that alpha 2 was equal to alpha 2 plus 2 alpha 4 is equal to b, alpha 3 plus alpha 4 equals to c minus b, and alpha 4 is a free variable. So we're going to set alpha 4 is equal to m. We set alpha 4 is equal to m, and then we write everything in terms of the free variable, and we have this. So here we can see that we can write any arbitrary vector from R3 as a linear combinations of these vectors that we were given in a set. So that means that the set that we are given, actually the set of vectors that we are given actually span R3. Okay, so we can say that U, which is equal to ABC transpose, can be written as a linear combination of the vectors in a set S. Thus S is a spanning set of R3. So that was the first problem. So question about this. Now the second one, let H be the set of all of the vectors of the form a minus 3b, a minus 3b, and b minus a, b, and transpose, where a and b are arbitrary scalars. In other words, we have this set. Show that H is a subspace of R4. Now the way you can easily do it is to actually use theorem 3-2-1. Normally if you have a question like this, you have to try to write this one as a linear combination of the vectors in R4, but an easier way to do it is to use theorem 3-2-1. So what does theorem 3-2-1 says? It says that if v1, v2, vn are element of a vector space, then the span, meaning that the linear combination of v1, v2, vn is a subspace of that vector space. In other words, if I have two vectors that belong to a vector space, or three vectors, or any number of vectors, any finite number of vectors that belong to a vector space, and if I can find if those vectors can be written as a linear combinations, then those vectors actually, like the set of all of the linear combinations of those vectors, is a subspace of that big vector space. So coming back here to this exercise, show that H is a subspace of R4. So what can I do? I know that H is a set of all of the vectors with four components of this form. Okay, a minus 3b, b minus a, and b. So let me take an arbitrary vector that belongs to H. Suppose that I take an arbitrary vector that belongs to H. Let's call it V. Now V can be written as a linear combination. So if I take V is equal to, I can separate. I can put the A's on one side, the B's on one side, and break it down this way. A multiplied by this plus B multiplied by this. So this one is a vector V1. This one is also considered as a vector V2. So I can see that if I take an arbitrary vector V from the set H, I can write it as a linear combination of two vectors that belongs to the vector space R4. Therefore, so I can see here that V is equal to A V1 plus B V2. So that means that H, that set H is actually the set of all of the linear combination of those two vectors V1 and V2. Okay, and then so that means that V1 is this one, V2 is this one, and those two vectors are elements belongs to the vector space R4. So then by the theorem 3-2-1, we can say that the span, meaning that the set of all of the linear combination of V1 and V2 form a subspace in R4. So here H, that was set that we're given, is actually the set of all of the linear combination of V1 and V2, and we've already defined V1 and V2 as these two. So here we can say that indeed H is a span V1 and V2. So that means that H is a subspace of R4. Okay, question about this one. So here's a matter of knowing the theorem and also knowing how to apply the theorem. Okay, one thing is to know the theorem, the other one is to know how you can apply the theorem. The next one, number 3, x1 is a vector, x2 is a vector, and then you have a vector x. The question is x belonging to the span of x1, x2? In other words, does this vector here x belong to the set of all of the linear combination of x1 and x2? So if we want to know if that vector x that is here belong to the set of all of the linear combination of x1 and x2, what can we do? We can actually we can try to write x as a in terms of x1 and x2. So we need to find coefficient alpha 1 and alpha 2 such that x is equal to alpha 1 multiplied by x1 plus alpha 2 multiplied by x2. So if those two coefficients exist, and I can write x1 and x2 in terms, if I can write x in terms of x1 and x2, given that this coefficient exists, then we can say that x belongs to the span of x1 and x2. So let's try to see if those coefficients exist. So what I do, I put alpha 1, I write alpha 1 x1 is this vector, plus alpha 2 x2, this vector is equal to x. And then here alpha 1 I multiply to this column here, alpha 2 to this column, and then I add things, and then I obtain this system. And I need to solve because my unknown is alpha 1 and alpha 2. I need to solve for alpha 1 and alpha 2. So when I solve, I obtain a contradiction here, and I have 0 is equal to 1, so that is a contradiction. So here we can see that there is no solution to the system, and the system is inconsistent. So that means that there is no alpha 1 and alpha 2 such that alpha 1 x1 plus alpha 2 x2 is equal to x. So that means that x doesn't belong to the span of x1 and x2. Okay, so that was about the homework. So any question about this? I think okay, hold on, it's coming. Okay, so homework 4. So every time someone does a homework, you receive some money. So homework 4 was done by Eunu. So she received. So for homework, you receive 250 francs CFA. So she received a 250 francs CFA. Hold on. What's going on? Yeah. All right. Okay. Okay, so let me go quickly review what we have done. We've seen that if I have, let's say I have two vectors, let's say v1 with coordinate, let's say 1, 2, and 3, and I have another vector v2 with coordinates 2, 1, 4, and 5, for example. If I have some coefficients, like I can have some coefficients alpha and beta, and alpha belongs to the set of real number and beta belongs to the set of real numbers. And if I write alpha v1 plus alpha beta v2, okay, I know that I can have like infinitely many values. For example, here I can replace alpha with 1, 2, 3, 4, 5, 6, 7. Similarly with beta I can replace it with whatever number I want from the set of real numbers. So so alpha v1 alpha 1, 2, 3 plus beta 1, 2, 1, 4, 5, they will form a set. Let's call that set H. Okay. So here this set represents all of the possible linear combination. So when we multiply a scalar by a vector like this and we are adding them together, we call them a linear combination. So the set of all of the linear combinations of two or more vectors is what we call the span. So that set H that represents the set of all of the linear combination of v1 and v2 can be written as span of v1 and v2. Okay. In some books, the notation, instead of writing parentheses here, they simply write span like this, braces v1 v2. Okay, so a span, remember that it is a set of all possible linear combination of v1 and v2. So in general, if I have, let's say a set like this, v1 v2 vn, and I have like alpha let's say alpha 1 v1 plus alpha 2 v2 plus plus alpha n vn, given that alpha 1 alpha 2 alpha n, all of them belong to the set of real number, they are scalars, then the set of all of the possible linear combination of this is called the span of v1 v2 vn. Okay, so that's like the concept of the span. We say that a vector belongs to a span a spanning set belongs to a vector space. Suppose that I have a vector space like R3. Suppose that graphically like this, I have a vector space like R3. Now if I take two vectors inside of R3, let's say I have v1 here, v2 here, I take two vectors in R3. If I can write so the set of all of the possible linear combination that I can form with those two vectors will form a subspace inside of that R3. We said that form a subspace. So the set of all of the possible linear combination, it will be like it will take in a space like this, something like this. So that will form a subset because you are combining those two vectors, and there are so many possible ways that those two can be combined. I can do 3 times v1 plus 2 times v2. I can do negative 1 v1 plus 2 times v2. So the possible combination will fill out this entire space. Okay, it will be like a huge space like this, and that form a subspace of this R3. Okay, so we've also seen that, and we've also talked about the null space. The null space, if I have an equation like this, ax is equal to b, ax is equal to 0, right? Now the set of solution. So suppose that I have an equation, a m by n system. So the set of solution, the solution set is the solution set of this system of equation will be inside of the null space of the matrix A. Okay, we call it the null of A. And we've seen that there is a relationship between the solution set of a system and the null space of that system. Suppose that I have ax equals to b, and that ax equals to b gives me a solution x0, meaning that if I plug x0 inside of this system, I find b. And suppose that ax equals to 0, I have the solution of this system gives me z. In other words, if I plug z in here, I get a 0. So so in other words, also that z belongs to the null space of A. Okay, so let me put in parentheses z, this vector here, this vector solution, such that A multiplied by z equals to z. This vector solution belongs to the null space of A. Now I said ax equals to z, so here ax equals to 0 gives me as solution a z. Z belongs to the null space of A. So if I add these two, I obtain a new solution is x0 plus z, and that new solution that I found, x0 plus z, is also a solution to ax is equal to b. Okay, so x0 is a solution of ax equals to b. Z is a solution of ax is equal to 0. Now if I do the sum of those two solutions, I will have a new vector, and now that new vector will be also a solution of ax is equal to b. Okay, so that's what we've seen also that concept. Now let's talk about linear independence. So that was about the review what we've seen last week. Now let's talk about the concept of linear dependence and linear independence. So suppose that I have two vectors like that in an xy coordinate. I have a vector x. This x is a vector, and I have another vector like this y. So we can see that, so here we said x and y are linearly independent. So x and y are linearly independent, meaning that if I do so they are not related, are linearly independent. Now let me show an example of linearly dependent. I have the vector x here and the vector y here. They are on the same line. I can always find coefficients. Y will be equal to some alpha x. Okay, I can actually relate those two. So it's like one can be written in terms of the other. So in that particular case, x and y are linearly dependent. Okay, so that's pretty much the concept of linear independence from a geometrical standpoint. Now suppose that I have a vector x3. x sub 3, x sub 3 is equal to 3 times x sub 1 plus 2 times x sub 2. So x sub 3 will be something like this. Suppose that x sub 3 is this vector -1, 3, and 8, and that is equal to 3 times another vector here, 1, -1, 2, plus 2, -2, 3, and 1. So here I can see that x3, I can see that x3 can be written in terms of x1 and x2. So let me write the set of all of the possible linear combination. So let us write the set of all linear combinations of x1, x2, and then x3. So I need to consider some coefficients, alpha 1 and alpha 2. So let alpha 1, alpha 2, and alpha 3 being real numbers, being scalars. So I have alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. That can be written in terms of x1 and x2 only, because I can replace x3 by x1 and x2. So that is equal to alpha 1 x1 plus alpha 2 x2 plus alpha 3, and I replace alpha x3 by this 3 times x1 plus 2 times x2. So I'm going to combine the like terms. So the x, so let me solve this. I'm going to have alpha 1 x1 plus alpha 2 x2 plus 3 times alpha 3 x1 plus 2 times alpha 3 x2. So I'm going to combine the x1s together and the alpha x1, the x1 together and the x2 together. So I'm going to have in the end alpha 1 plus 3 times alpha 3 x1 plus alpha 2 plus 2 times alpha 3 x2. So here I have alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 equals to that. In other words, the set of all of the possible linear combination of x1, x2, and x3 can be summarized, can be simplified by writing it as a set of linear combination of x1 and x2. In other words, the span of x1, x2, and x3 is equal to the span, the set of all the possible linear combination of x1, x2, and x3 is equal to the span of x1 and x2. So we can also see that I can write x1 in terms of x2 and x3, and I can also write x2 in terms of x3 and x1. So I can, if I continue the demonstration, I will see that the span of x1, x2, x3 is equal to span of x1, x2 is equal also to the span of x1 and x3, and it is equal to the span of x2 and then x3. So here we can see also we can see that there is a dependency. One vector is written in terms of the other. There is a dependency relationship between those three vectors, x1, x2, and x3. One can be written in terms of the other. So there is a dependency relationship between the two, and also we can easily simplify. We can simplify vectors that are linearly dependent. We can simplify them. So now that leads us to the definition of linear dependency. So as we can see, if I have x1, x2, and x3, and if I write it, so x, I can write 3x1 plus 2x2 plus 2x2 minus x3 equals to the 0 vector. In other words, 3 times x1 is this one, plus 2 times x2 minus x3. x3 is negative 1, 3, and 8. If I combine those three vectors, I get the 0 vector like this. Okay, so the definition of so here is 1, the coefficient here is 1. So we can say that three vectors, so let's call this one is x1, x2, and then x3. So vectors v1, x1, x2, and x3 are linearly dependent if the coefficients that are here are not zero. Not all of them are zero. So some of them can be zero, probably one of them can be zero, or two of them, a couple of them, but not all of them have to be zero. So it's like the coefficient here are non-zero, so the linear combinations is equal to the 0 vector. So let me restate that again. For linearly dependent, so these are linearly dependent. So x1, x2, and x3 are linearly dependent if the coefficient, if we can write the linear combination such that the linear combination would be equal to the 0 vector if and only if the coefficients associated with those vectors in the linear combination are not equal to 0. Not all of them are equal to 0. Now if it was for linearly independent, for example, suppose that I have a vector v1 alpha plus beta v2 plus gamma v3 equals to 0. That implies that the coefficient here has to necessarily be, all of them are equal to 0. For this to be true, for this linear combination to be equal to 0, all of them here has to be equal to 0. Okay, so if alpha equals to beta is equal to gamma, and that is equal to the is equal to 0, then so it's like, so if this is equal to 0, then v1, v2, and v3 are linearly independent. So for linear independence, if you need all of the coefficients to be equal to 0. But for linear dependence, the coefficients do not necessarily have to be equal to 0. Okay, so that you have a linear dependency. So that's kind of like the concept in a nutshell of linear dependence and independence. Question about this? Suppose that I have n vectors in Rn. Suppose that I have vectors x1, x2, dot 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 xn. These are n vectors in Rn. Now if I calculate the determinant, if the determinant of the matrix that I can form with x1, x2, xn is equal to 0, then x1, x2, dot 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 xn are linearly dependent. Now if it is different from 0, of course it is linearly independent. So suppose that I have k vectors. So suppose instead of having n vectors, suppose that I have k vectors. Suppose so that here you have like a n by n matrix. Suppose you have k vectors in Rn. So in this case you can no longer use the determinant to find a solution, x1, x2, xk. Now if you want to determine whether these vectors are linearly independent, you need to set c1 coefficient 1 x1 plus c2 x2 plus ck xk equals to 0. Now you need to find the value of this coefficient. Now if it is linearly independent, those coefficients, all of them are going to be equal to 0. But if it is linearly dependent, you notice that some of those coefficients will not be equal to 0. Okay. So here you solve, this is equivalent to solving x c equals to 0, and here we have two cases. We have in a row echelon form, we have three variables in row echelon form. So if there are three variables, so that means that we have a non-trivial solution. The trivial solution is the solution 0, 0, 0. If you don't remember, the trivial solution was the solution 0, 0, depending on the type of system. Suppose that I have a system with k values. So here I'm going to have k zeros, for example. So the free variable, if I have free variables, so that means that I have a non-trivial solution. Now suppose if I have a non-trivial solution, that means that I will have some coefficient here that are not equal to 0 because I have some free variable. So the vectors are linearly dependent. Okay. Now suppose also that I have solved this system, and in row echelon form there is no free variable. So that means that the only solution is a trivial solution. So that part C here is equal to 0. So that means the vector C that contains those coefficients here, all of this is 0. The 0 vector, the trivial solution, and because we have the trivial solution, that means that the vectors are linearly independent. Okay. So let me summarize again. So to determine whether, from calculation, to determine whether is we have vectors that are linearly independent or dependent. If we have like if those vectors, suppose that we have n vectors in Rn. Okay, so suppose that I have, let's say 1, 1, 0, 1, 1, 3, 1, 2, 3. So here we have vectors with three components in it. So that means that we are in R3. Okay, the set of R3 is a set of all of the vectors with three components. And here I have three vectors, exactly three vectors in R3. So in that case, I can use determinant to find the solution. I can use the determinant. I'm going to combine those vectors into a matrix, and then I'll calculate the determinant to determine if these vectors are linearly dependent or independent. So I'll have something like this, and then I calculate the determinant, and the value that I found, if it is equal to 0, that means that it is linearly dependent. If it's not equal to 0, it's linearly independent. Now suppose that I have in R3, still in R3, suppose that I have 4 vectors. So now here the number of vectors do not match the dimension of my space. So suppose that I have 1 1 0 1 2 3 4 5 5 6 7 and 1 2 0. Now I can no longer use the technique of determinant because I have a 3 by 4 matrix. The determinant works on n by n matrices. So in that case, I need to solve the system. The system, I need to write it as a system 1 1 0 1 2 3 5 6 7 1 2 0, and then I need to solve for x that is for c that is here. And now if I have free variables, in my row echelon form, I have the non-trivial solution. That means that the vectors are linearly dependent. If there are no free variables, that means that the vectors are linearly independent. Okay, so that's the way we can solve it. So question about this. So let's go to the notes.
So you said?
I was wondering if you had questions. Okay. Now let's go to here.
I don't know questions, sir.
Okay, no problem. Okay, it is coming. It's kind of slow. I'm trying to share my screen and it's kind of slow, but it is coming. Okay, so now let's go to the note. Linear independence. Consider the following vectors in R3. x1, x sub 1 is equal to 1 minus 1 2, x2 is equal to this, x3 is equal to this. Let S be the subspace of R3 spanned by x1, x2, and x3. Okay, so I was saying that was saying that okay, so let S be the subspace spanned by these three vectors. Actually, S can be represented in terms of two vectors x1 and x2, since the vector x3 is already in the span of x1 and x2. That is, x3 is equal to 3 times x1 plus 2 times x2. So you see the vector x3 that is here, this can be written as a linear combination of x1 and x2. If I put 3 here, and I put 2 here, and I add them up, I find the value of x3. So any linear combination of x1, x2, and x3 can be reduced to a linear combination of x1 and x2. So if I take any coefficient alpha sub 1, alpha sub 2, and alpha sub 3, I want to write a linear combination of x1, x2, and x3. I'll obtain the following, and I can actually replace x sub 3 by its value in terms of x sub 1 and x sub 2, and I replace it with 3x sub 1 plus 2x sub 2, and if I rearrange the terms, I obtain alpha sub 1 plus 3 alpha sub 3 x1 plus alpha sub 2 plus 2 alpha sub 3 x2. So in other words, the set of all of the linear combination of x1, x2, and x3 is equal to the set of all of the linear combination of x1 and x2, because you can actually rewrite x1, x2, and x3 in terms of simply x1 and x2. So equation number 1 can be written in form 3x1 plus 2x2 minus x3 equals to 0. So when we're talking about equation number 1, we're talking about this one here. If I take the x3 and I bring that on this side of the equation, I obtain this equation over here. Since the three coefficients are non-zero, we could solve any vectors in terms of the other two. So x1 can be written in terms of x2 and x3, x2 can be written in terms of x1 and x3, and x3 can be written in terms of x1 and x2. So it follows that the span of x1, x2, and x3 is equal to the span of x2, x3, and the span of x1, x3, and the span of x1 and x2. So because of this dependency relation, the subspace S can be represented as the span of any two given vectors. Okay, so before I even continue, typically in data science, for example, if you are working with data, you have vectors like your data entries, the columns of your data. They are represented by variable like x1, x2, and x3. So the first step usually in when you are analyzing data will be to actually reduce the dimensions. So the way we'll be reducing the dimension, there are some techniques for reducing dimensions in data science, and the principle behind those dimensionality reduction is based on that principle. Like if I have three vectors, instead of writing them all of them, I'm going to use like the minimal number of vectors that best represent those three vectors. Okay, so and the reason why people reduce the dimension is because we do not want the result to be wrong. Usually when you have too many variables that contain the same information, or that are related, your analysis may lead you to wrong results. So that's why it's important to reduce the dimension, and the techniques to reduce the dimensions are based on this principle in here. Now let's continue. We can generalize this example by making the following observations. If v1, v2, vn span a vector space, in other words, v1, v2, and vn can be written as a linear combination of any vectors in that vector space, and one of these vectors can be written as a linear combination of other n-1 vector, then those n-1 vectors span v. Now given n vectors v1, v2, vn, it is possible to write one of the vectors as a linear combination of the n-1 vectors if and only if there exist scalars c1, c2, cn not all 0, such that C1 plus V1, C1 multiplied by V1 plus C2 multiplied by V2 plus dot 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 Cn multiplied by Vn is equal to the 0 vector. In other words, for linear dependence, just like in the previous case, if there exist coefficients such that not all of them are 0, and we obtain a 0 here, then we can say that they are linearly dependent. Now here, definition: vectors v1, the vectors v1, v2, dot 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 vn in a vector space V are said to be linearly independent if their linear combination is equal to 0, implies that all of the scalars that are here, C1, 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 C2, C3, all the way to Cn, all of them are equal to 0. So implies that all scalars C1, C2, dot 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 Cn must be equal to 0. Now, if V1, V2, dot 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 Vn is a minimal spanning set, then V1, V2, dot 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 Vn are linearly independent. Conversely, if V1, V2, dot 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 Vn are linearly independent and they span V, then V1, V2, dot 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 Vn is a minimal spanning set for V. A minimal spanning set is also called a basis. I think in the next section we're going to learn more about basis. Yeah, so here let's work on this one. Are the vectors 1, 1 and 1, 2 linearly independent? So let me solve this. So here the question is, in this example I have these two vectors 1 1 and 1 2. So what I can do is to simply do, here I notice that this can form a 2 by 2 matrix. They can form a 2 by 2 matrix. So normally if I want to finish it quickly, all I can do is to do this 1 1 1 2 like this and write 2 minus 1, so 2 here and then minus 1 here. I get 1 not equal to 0, so these two vectors are linearly independent. So 1 1 and 1 2 are linearly independent. Okay, but suppose that we do not know how to use suppose that we don't know that if we calculate the determinant and if the determinant is not equal to 0, then it is linearly independent. The question is, how do we do it? So in that case, so second way, let C1, C sub 1, C sub 2 be real scalars, and we want to find C1 and C2 such that C1 1 1 plus C2 1 2 equals to the 0 vector. That's our goal. So I'm going to calculate. So this implies that, so C1 1 1 plus C2 1 2 equals to the 0 vector. It's equivalent to saying that C1 here plus C2 here, 2 times C2 is equal to 0, 0, and I'm going to add them. My goal is to find the values of C1 and C2. I'm going to add them. C1 plus 2C2 like this equals to 0, 0. So this implies that C1 plus C2 equals to 0, and C1 plus 2C2 equals to 0. We can put that into a system if you want to. So I have 1, 1, 1, 2, 0, 0. If I do negative row 1 plus row 2 to obtain a new row 2, I have the following: 1, 0, 1, 1, 0, 0, and I continue. I do negative row 2 plus row 1 to obtain a new version of row 1, and I obtain here, I have 1, 0, 0, 1, 0, 0. So here I can see that C1 is equal to 0, C2 is equal to 0. So here C1 equals to 0, C2 equals to 0. So we can see that the only way this is true, this linear combination is true, it is only if C1 equals to 0, C2 equals to 0. Therefore, um, therefore, um, therefore, the C1 equals to C2, which is equal to 0. Thus, the vectors 1, 1 transpose, 1, 2 transpose are linearly independent. Here I could have, in this particular instance, here I could have noticed that I could have just looked at the system and realized, even here I could have looked at the system and realized that we have no free variables. There is no free variable. So here is a case like this. There is no free variable. So that means that the only solution that is possible is a trivial solution. So the vectors are linearly independent. So we could have also stopped right here without even continuing, and then say that there is no free variable, etc., etc. So that was one of the examples. Question about this?
No, sir.
Alright.
No, sir.
Alright. Now I think there is another exercise. Let's see. So yeah, so that was the first question here. Now, definition. The vectors v1, v2, vn in a vector space V are said to be linearly dependent if there is a scalar c1, c2, cn not all 0 such that their linear combination are equal to 0. Now, let x being this vector 1, 2, 3 transpose, are those vectors e1, e2, e3 linearly dependent with x? So the way we can actually determine that is to try to see if their linear combinations, like x plus e1, e2, e3, if the linear combination is equal to 0, and if that implies that the coefficients associated with those linear combination, with that linear combination, is all of those coefficients are zeros. So let's try to solve this. So here let us so we here we have x equals to 1 2 3 transpose, that is x, and E1 it is actually 1 0 0. E2 is actually 0 1 0. E3 is actually 0 0 1. So here what we want to see if there exists some coefficient alpha such that those alphas are not, if all of those alphas coefficients that are forming a linear combination with those four vectors, if that all of them are zeros, then we can say that these vectors are linearly independent. So let us find scalars C1, C2, C3, C4 that belongs to the set of real numbers such that C1 E1, okay, this is the vector E1, plus C2 vector E2 plus C3 E3 plus C4 vector X will be equal to the 0 vector. So in other words, C1 E1 plus C2 E2 plus C3 E3 plus C4 E4 X 1 2 3 equals to the 0 vector, which is 0 0 0. So I'm going to have the following so C1 multiply here, I have C sub 1, C1 times 0 0, C1 times 0 0. So here I have C1 0 0 plus C2 times 0 and C2 times 1 and C2 times 0 plus 0 here plus 0 here plus C3, and finally C4 here plus 2 C4 plus 3 C4 4 equals to 0 0 0. And here I have C1 plus C4, here I have C2 plus 2 C4, and here I have C3 plus 3 C4, and that is equal to 0 0 0. Normally we have to solve the following system. Here we have we are looking for C1 C2 C3 and then C4. So here we have 1 times C1, it's like, so let me write all of these in terms of coefficient, in terms of a system. So I'm going to have the following it's like C1 plus 0 C2 plus 0 C3 plus 1 times C4 equals to 0. Here 0 C1 plus 1 C2 plus 0 times C3 plus 2 times C4 equals to 0, and 0 C1 plus 0 C2 plus 1 times C3 plus 3 times C4 equals to 0. I can put that into a system: 1 0 0 1 0 1 0 2 0 0 1 3. I augment it with these zeros and I solved. As you can see, we're going to have three variables. Okay, we're going to have three variables. So just by that, we can say that the system is linearly independent. But if we solve, we're going to find that C1. So by solving, we can have a C1 that is equal to 1. This can be one solution. C2 can be equal to 2. C3 equals to 3. C4 can be equal to -1. So that means that I can find some values. So here I can have 1 times E1 plus 2 times E2 plus 3 times E3 minus 1 times X equal to 0. So the vectors E1, E2, E3 and X are linearly dependent if all of those coefficients zeros were C1, C2, C3 and C4, if all of them were 0, 0, 0, 0, 0, all of them, then it is linearly independent. If two of them are 0, suppose that I have 0 here, 0 here, but here I have 3, 1, 3 and -1 like this, it is still linearly dependent, because for it to be linearly independent, all of them have to be equal to 0. Suppose that I have 0 here, 0 here, 0 here, but this one is different from 0, it is still linearly dependent. Okay, the only way it is linearly independent if all of the coefficients are all zeros when you set a linear combination of those coefficients being equal to 0. So that was the second example. So here the question was, are the vectors linearly dependent with X? The answer was yes, and we've shown that. Now here, if there are non-trivial choices of scalars, when we're talking about non-trivial choices, it's about meaning that the values that we select are zeros. If we take values of the scalars, if we choose values of the scalars such that they are non-zeros, okay, if there are non-zero choices of scalars for which the linear combinations c1 v1 plus cn vn is equal to the 0 vector, then v1 vn are linearly dependent. If the only way the linear combination c1 v1 plus cn vn can be equal to 0, can equal the 0 vector, is for all of the scalars here to be equal to 0, then you can say that v1 and vn are linearly independent. Now, geometric interpretation. If two vectors in R2 are linearly dependent, one of the vectors can be written as a scalar multiple of the other. Thus, if both vectors are placed on at the origin, they will lie along the same line. So example here, we can see that x1 and x and y are linearly dependent. So here's the vector x, here's the vector y, and here x and y are linearly independent. We can see x is here, y is here. Now theorem 311. Let x sub 1, x sub 2, x sub n be n vectors in Rn, and let x be a matrix formed by the vectors x1, x2, xn. The vectors x1, x2, xn will be linearly dependent if and only if x is singular, And remember, X is singular if its determinant, if a matrix is singular if its determinant is equal to 0. Okay, so if the determinant of a matrix is equal to 0, then the vectors in its column are linearly dependent. Okay. Now here we have determine whether the vectors 4, 2, 3 transpose 2, 3, 1 and 2, negative 5 and 3 are linearly dependent. Okay. Okay, so let me try to solve this. Okay, now this one is pretty straightforward. I have some vectors here. So let me write the definition. By the definition, the theorem that I have, the theorem says that I have a set of vectors like this: x1, x2, dot 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 xn, and these vectors will be linearly independent. So x1, x2, and those vectors belongs to Rn, and we say that x1, x2, dot 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 xn are linearly dependent if and only if the matrix that has been formed by those vectors, if we insert them into a column, if that matrix is singular. In other words, the determinant of that matrix has to be equal to 0. So here we have three vectors, 4, 2 and 3, and we have 2, 3 and 1, and we have 2, negative 5 and 3. So what we need to do, if we can put them inside of a matrix, we can create a matrix A that represent those. So we can say let A be a matrix such that A is equal to this. Now we can find the determinant of the matrix A. We put a so 4 here, 3, negative 5, 1, 3. Here minus 2, 2, negative 5, 3, 3, plus 2, 2, 3, 3, 1. And when we solve this, I have 4 here, 9 plus 5, minus 2, 6 plus 15, plus 2, 2 minus 9, and I have 0. Okay, so we can see that the determinant of the matrix formed by these three columns is simply 0. So that means that the vectors 4, 2, 4, 2, 3, 2, 3, 1, and 2, negative 5, 3 are linearly dependent. Okay. All right. Now the next Okay, so here we've actually done this exercise, this one. Now the next one, to determine whether k vectors x1 x2 all the way to xk in Rn are linearly independent, we can rewrite the equation c1 x1 plus c2 x2 plus dot 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 plus ck xk is equal to 0 as a linear system x c equals to 0, where x is equal to x1 all the way to xk. And if k is not equal to n, then the matrix is not a square matrix, so we cannot use the determinant to decide whether the vectors are linearly independent. Now the system is homogeneous, so it has a trivial solution c equal to 0. It will have non-trivial solution if and only if the row echelon form of x involve the free variables. If there are non-trivial solutions, then the vectors are linearly dependent. If there are no free variables, then c equals 0. So the column of the coefficients, c is the column representing all of the coefficients, is equal to 0 is the only solution, and hence the vectors must be linearly independent. I think that this is what I was actually saying. Let me show you. So that paragraph that I've just read, I think I've talked about it already, and that was yes, so that was what I was saying in here. So the paragraph that we just read has been summarized in here. Suppose that you have k vectors in Rn, and those k vectors are x1 x2 all the way to xk, and suppose that you have c1, you have these linear combinations. Now if you want to find whether these vectors are linearly independent, we need to set this. Now c that is here is actually the vectors that contains these values c1 c2 c3 all the way to ck, that vector c here. X is the coefficient matrix, and then if we try to solve this, if you have some free variables in a row echelon form, then you have the non-trivial solutions, the vectors are linearly dependent, and no free variables, that means that you have the trivial solutions, and the vectors are linearly independent. And that's what I was that's a summary of the paragraph that we've just read. So this paragraph here has been summarized. Now here, determine whether the vector x1 x2 and x3 are linearly independent. So we have these three vectors, and we want to know whether they are linearly independent. As you can see here, if we insert them into a matrix, we'll have a 4 by 3. So in that case, I cannot use the determinant of the matrix. So I need to actually solve a system of linear equation. So it will lead me to solve the following. It will lead me to solve the following. I have x1 equals to negative 1 here, 1 here, 2 and 3. And I have x2 equals to negative 2, 3, 1 and negative 2. And I have x3 equals to 1, 0, 7, 7. Okay. Now I can actually write them as, so that lead me to solve the following. What I can do is to set c1 x1 plus c2 x2 plus c3 x3 equals to the 0 vector. So here I have, let c1 c2 c3 be real scalars, and I set this equals to 0. So that will lead me to actually, so if I was writing it, I can actually write it as 1, negative 1, 2, 3 plus negative 2, 3, 1, negative 2, C2 plus C3 1077 equals to 0, 0, 0, 0, like this. Okay, so that leads me to this, and that actually lead me to actually solving the system, the following system, with this following system of equation, which is 1, negative 1, 2, 3, negative 2, 3, 1, negative 2, 1, 0, 7, 7, 0, 0, and that will give you, so if you try to solve this system, that will give you the values of C1, C2, C3, and C4. So if we reduce it, I'm going to skip the step, I'm going to put the result. If we do the row echelon form, we obtain something like this: 1, 0, 0, 0, negative 2, 1, 0, 0, 1, 1, 0, 0, and here we have 0, 0, 0, 0. So here we have a pivot position, pivot position. So here the row echelon form, involves a free variable. Okay, so remember, this one is your C1, this one is for C2, and normally this column is for C3. So we can see that C1 and C2 have a pivot position, but C3 involve a free variable. Okay, so the row echelon form involves a free variable C3, and so there are non-trivial solutions. So if you have a free variable, that means that you have a non-trivial solution, and hence the vectors x1, x2, and x3 must be linearly dependent. Alright, so that was about the concept of linear dependence and independence. I think that there is one more passage that we need to cover. So that's the example that we have done. Now theorem 332, let v1, v2, vn be vector in a vector space. Now a vector, suppose that we take a vector v, and that vector v belongs to the span of v1, vn. In other words, that means that that vector v belongs to the set of all of the possible linear combination of v1 and all the way to vn. So a vector v that belongs to the span of v1 all the way to vn can be written uniquely as a linear combinations of v1 to vn if and only if v1 all the way to vn are linearly independent. So if I have a vector v that belongs to the span of v1 all the way to vn, and I can have, if that vector form a linear combinations with the vectors inside of that span, now that linear combination will be unique if and only if the vector v1 all the way to vn are linearly independent. Okay, so that's what this theorem is actually saying. Okay, so any question about this? Okay. now let's move on to the next topic. Okay, before I even move to the next topic, let me give you an example of this really quick. Suppose that I have okay, suppose that I have suppose that I have two vectors v1 and v2. v1 is actually 1 0, v2 is actually 0 1, and so actually this one is e1. This vector here is actually e1, and this one is actually e2. So graphically I have something like this, 0 1. This vector here is e1, and this vector here, so and this vector here is e2. And if I so here these two vectors, so v1, let me write v1. So I'm going to v1, just to be faithful to the theorem, v1 and v2, these two vectors belong to a vector space. So v1 and v2 here, v1 v2 belongs to the vector space R2, the set of all of the the set of all of the column vectors that has two components. And these vectors, we can show that, we can demonstrate. I think that there was one exercise where that was demonstrated. So suppose that I take a vector v that belongs to the span of e1 and e2. That means that vector v can be written as a linear combination of e1 and e2. So suppose that I have a vector v that is 2 e1 plus 2 e2, something like this. So the vector v would be 2 times 1 0 plus 2 times 0 1, and I have here 2 2. Okay, so 1 here 2, 1 here 2. So this is my vector v here. So according to the theorem, and also according to the theorem, this linear combination that I have here, v, which is equal to the linear combination of e1 and e2, will be unique if and only if those two vectors here, e1 and e2, or v1 and v2, are linearly independent. Okay, so so if it's linearly independent, this is not going to be unique. I'm going to have multiple ways of having the same thing here. Okay, but if I have this one to be unique, that means that these two are linearly independent. And the way I can show that these two vectors are linearly independent is to find the determinant. So if I write the determinant of e1 and e2 here, determinant e1 e2 is going to be equal to 1 0 0 1. I'm going to have 1 minus 0, I get 1. So as you can see, um, this is so E1 and E2 are linearly independent. Thus, the linear combination that we have here is unique for V, the vector V that we have here. That linear combination that was obtained by this combination of two vectors is unique. There is no other way you can be able to find something like that. Okay, so that's what this theorem, the previous theorem was actually telling you. Okay, this previous theorem in here. Yeah, this one, let v1 v2 that vn, we took the case of two vectors instead of having n vectors. Being a vector space v, we took a vector space r2 and a vector v that belongs to the span. So the vector v that belongs to a set of linear combination of v1 and v2 can be written uniquely as a linear combination of v1 all the way to vn if and only if v1 all the way to vn are linearly independent. So in our case, we took two vectors in the vector space R2 and we selected a vector space, a vector v that belongs to the span of v1 and v2, and we have seen that we can write v1 and v2 as a linear combination of v, and we also did find that v1 and v2 that we have selected were linearly independent. So our linear combination that we have found is unique. Alright, so any question about this section? Now let's move on to the next topic. Okay. Okay, so the next topic is the concept of basis and dimension. So I think let's take a break and resume at let's take a 15-minute break and resume at 11:21. Okay, so we resume at 11:21.
Okay, sir.
Okay. let us alright, so let's resume. We were about to talk about basis and dimension. So the concept of basis is pretty straightforward. It builds on what we've already seen. So we've talked about linear independence, and we talked about spanning sets. And here, if you have a vector space, you have some vectors v1, v2 all the way to vn that are linearly independent. v1, v2 all the way to vn are linearly independent. That's the first condition. Second condition is that in like v1, v2 all the way to vn span the vector space span v. In other words, so the span of v1, the set of a linear combination of v1 all the way to v2 will be able to form the entire vector space v. Okay, so suppose that you have v1, v2 being elements of a vector space v, and v1 all the way to vn are linearly independent, and v1 and the span of v1, v2, the set of all of the possible linear combinations from the entire vector space, then you say that v1, v2, vn form a basis for the vector space v. The simplest basis that we can think of, if you have something like this, you have these two vectors e1, which is your 1 0, and you have e2, e1 is this one, and you have e2 here, which is your regular 0 1. This is your e2. So e1 and e2, we've seen previously that they were linearly independent. And secondly, we can actually we can pick up any vectors in R. Actually, e1 and e2 belongs to R2. They belong to the vector space R2, and like we can pick up any vectors in R2. So suppose that I take any arbitrary vector in R2 like this. I can write that vector as a linear combination of e1 and e2. So here a e1 plus b e2, so we can say that span of e1 e2 is equal to the entire vector space R2, because I can pick up any vector from that vector space and write it as a linear combination of e1 and e2. So the first condition, e1 and e2 being linearly independent, is met. The fact that e1 and e2 can form the span of e1 and e2 form the entire vector space, we can conclude that e1 and e2 form a basis for R2. As simple as that. Alright. So that's in a nutshell the concept of basis. So now let's go to the notes. Definition. So basis and dimension. The vectors v1, v2 all the way to vn form a basis for a vector space v if and only if 1. v1, v2 all the way to vn are linearly independent, and 2. v1, v2 all the way to vn span v. To put it simply, a basis can be understood as independent vectors that span the space. So basis for a vector space is a sequence of vectors with two properties. The first property, the basis vectors are linearly independent, and the second is that they span the space. The standard basis for R3 is E1, E2, E3. The basis is not unique. Indeed, there are many bases that we could choose for R3. For example, 1 1 1 0 1 1 2 0 1 and this one. Both are bases for R3. Theorem 341. If v1, v2, vn is a spanning set for a vector space v, then any collections of m vectors in v where m is greater than n is linearly dependent. So that means what? I know that these vectors can be written as a linear combinations of any vectors of the entire space. So if the vector space can be written with those n vectors. Suppose that I can write it with two vectors. Okay, the entire vector space can be described as a linear combination of two vectors. Suppose e1 and e2. Now, any spanning set. So any vectors that is coming from this set. Like let's suppose that I take an extra vectors that is coming from this set, and I try to actually find to find if there is a linear dependency. I will find a linear dependency if I take any other vector more than the total number of vector that forms that is spanning the entire vector space. Okay, so suppose that I can span the entire vector space with only two vectors from this set, and then I take another vector from that same vector space, and I try to see if they are linearly dependent or independent. I'll find that they are linearly dependent. So that's what this theorem is saying. Corollary: suppose that v1 all the way to vn and u1 all the way to um, both of them are bases for a vector space. As a result of that, if this one is a basis, this one is also a basis. That means that the number of vectors that are here I have n vectors, here I have m vectors. That means that the number of vectors in both sets are the same. So here that means m is equal to n. Okay, n is equal to m. Definition: let V be a vector space if V has a basis consisting of n vectors. We say that V has dimension n, and the subspace 0 of V is said to have dimension 0. Now V is said to be a finite dimensional if there is a finite set. So here is a set. The word is missing is set of vectors that span V. Otherwise, we say that V is infinite dimensional. So here is a definition of the dimension. The dimension, if you have a basis that has n vectors. So for example, here this basis has n vectors. In that case, we say that the dimension of this basis is n. Okay. Theorem 343. If V is a vector space of dimension greater than 0, n greater than 0, then 1. Any set of linear combinations, any set of linearly independent vectors span V. Okay. And then 2. Any n vectors that spans V are linearly independent. Okay, so if, for example, if V is a vector space, let's say that V is a vector space R2, for example. Now any set of two linearly independent vectors will span V. Okay, and any n vectors that spans V are also linearly independent. Okay, for example, in R2, if I take two vectors that are linearly independent in R2, automatically those two vectors will be spanning the entire R2, and any two vectors that spans the entire R2 is considered linearly independent. Now theorem, that was theorem 343. If V is a vector space of dimension n greater than 0, then no set of fewer than n vectors can span V. So you cannot have so it's like your basis, your like V is a vector space of dimension n. So that means that you have like it is spanned by n vectors. Okay, now like it's impossible for you to have vectors that are less than n that can actually span your vector space. And now any set of fewer than n linearly independent vectors can be extended to form a basis for V, and any spanning sets containing more than n vectors can be pared down to form a basis of V. Now standard basis. So we refer to E1, E2 all the way to A1, E2, and E3 as the standard basis for R3. More generally, for standard basis for Rn is the set E1, E2 all the way to En. Now, the most natural way to represent matrices in R2 by 2 is in terms of basis E sub 1 1, E sub 1 2, E sub 2 1, E sub 2 2. So this is then the standard basis for R2 by 2. Remember, R2 by 2 is a set of all 2 by 2 matrices. So the set or the collection of all of the possible 2 by 2 matrices that can exist. Now we can form a like there is a basis also for that. That set has a basis, and that is given by these matrices. We'll see them in the example below. This is the standard basis for R2 by 2. Now the standard representation for a polynomial, the standard way to represent a polynomial in terms of function. Okay, the standard way to represent a polynomial in Pn. So here is like a polynomial of degree n in terms of of the function 1 x squared xn. Thus the standard basis for Pn is this 1 x squared all the way to xn. So as you can see, basis is not only restricted to vectors. The concept can be extended to matrix, and the concept can be also extended to polynomials. Okay, and here is like an example with polynomials of degree n. Now example, let's look at this example. Example 2. In R2 by 2, consider the set E sub 1 1. Consider the set E sub 1 1, E sub 1 2, E sub 1 2 1, E sub 2 2, where E sub 1 1 is this, E sub 1 2 is this. Show that E1 all the way to E2 2 are linearly independent, and show that these matrices form a basis for R2. So let's try to work on this. Okay, so here we have so in the first case, E11, so E11 is actually it's like you have it's like this matrix 1 0 0 0. So here you can notice that the 1 is positioned in the first row, first column. E12, you have, so that means your 1 is supposed to be in the first row, second column. First row, second column, I put the 1 here, and everything else is a 0. And E, so 1 1 1 2 2 1 2 1. That means my 1 is positioned in the second row, first column, and everything else is a 0. And E2 2, that means my 1 is positioned in the second row, second column. Okay, so the first question was to show that E1, E12, E21, E22 are linearly independent. So the way independent, usually we do it with vectors. We have a vector and then we show that the vectors are linearly independent. In this case we have 2 by 2 matrices. So what we need, the principle is the same. As long as we can find a set of scalars alpha 1, alpha 2, alpha 3 all the way to alpha 4, such that the linear combination of these coefficients and these matrices is going to be equal to 0, and the coefficients are all 0, then we can say that these are linearly independent. So that's what we're going to do. So here we're going to say the following. Let C1, C2, C3 and C4 be scalars. Okay, and we want to see if those scalars are all equal to so let us set the following: C1 E11 plus C2 E12 plus C3 E21 plus C4 E22 equals to 0, the 0 matrix. Here it's a 0 matrix, and here we're going to have the following: C11. So let's solve for C1. Let's solve for C1, C2, C3 and C4. So we have C1 E11 plus C2 E12 plus C3 E21 plus C4 E22 equals to the 0 matrix. That is equivalent to C1 1 0 0 0 plus C2 0 1 0 0 plus C3 0 0 1 0 plus C4 0 0 0 1 equals to the 0 matrix 0 0 0 0. And when we solve that, we have here C1 0 0 0 plus here 0 C2 0 0 plus here 0 C3 0 0 plus here 0 0 0 C4 equals to 0, 0, 0, 0, like this. Now I'm going to add all of them, all of the entries. I'm going to have C1 plus 0 plus 0 plus 0, that is C1. So C1, C2, C3, C4 equals to 0, 0, 0, 0, 0, 0, 0, 0. So here you can clearly see that C1 equals to 0, C2 equals to 0, C3 equals to 0, C4 is equal to 0. So that implies that C1 equals to 0, C2 equals to 0, C3 equals to 0, and C4 equals to 0. So here we can say that so here, since C1 E11 plus C2 E12 plus C3 E21 plus C4 E22 equals to 0, implies that C1 equals to C2 equals to C3 equals to C4, which is equal to 0. Then the matrix is E11, E22, E12, E21, and E22 are linearly independent. Okay, so that was the first question. Now the second question, we want to show that that's the first question. The first question was to show that E1, E2 all the way to E22 are linearly independent. Now what we want to show that is that we want to show that we want to show that E11, E12, E21, and E22 form a basis for R2 by 2. So here what we can do is to consider an arbitrary matrix. You can select an arbitrary matrix from the set from this space, from this vector space. You can select an arbitrary 2 by 2 matrix from that vector space, and then with that vector space we can actually show that vector space, that arbitrary matrix span the entire vector space. We can do that, but there is one theorem that we have previously seen, and that theorem says that, so let me go here and write. So from here we can say that so E1 that are linearly independent, and since they are linearly independent, we can yeah, so these are linearly independent. We already said that. Now what we can do, that means that we can write them as a linear combinations. Okay, so let me take a vector, a matrix from R2 by 2. So let A be an arbitrary matrix belonging to R2 by 2, that belong to the set of all of the 2 by 2 matrices. So what I can say is that A equals to A sub 1 1, A sub 1 2 a sub 1 3 a sub 2 2. Okay, so let's alpha 1, or C1 if you prefer, alpha 1, alpha 2, alpha 3, and alpha 4 be scalars. Okay, and real scalars be real scalars, and a11, a12, a13, and a22. All of these belong to the set of real numbers. So now let's look at let's find alpha 1, alpha 2, alpha 3, and alpha 4 such that the matrix A is like a linear combination of these vectors here. These not vectors but matrices here. Alpha 1 E1 E11 plus alpha 2 E12 plus alpha 3 E21 plus alpha 4 E22. So if you are capable of finding coefficient alpha 1, alpha 2, alpha 3, alpha 4 such as we have this, then we can say that these matrices actually span. These matrices actually span R2 by 2, and if they span R2 by 2, in addition to the fact that they are linearly independent, they form a basis. Okay, so we said this. Let A being a let's see if we can write A, an arbitrary matrix from R2 by 2, as a linear combinations of these matrices. So A will be equal to alpha 1 E11 is that 1 1 0 0 0 plus alpha 2 here 0 1 0 0 plus alpha 3 0 0 1 0 plus alpha 4 0 0 0 1. So let me write A here. A is actually A11, A12, A13, A22. And if I do so, here is what I get. So A11, A12, A13, A22. So that alpha comes in here, alpha 2 comes in here, alpha 3 comes in here, alpha 4 comes in here. So I'm going to have the following: alpha 1 0 0 0 plus alpha 2 here plus alpha 3 here plus alpha 4 in here, and I do the sum of these matrices: A11, A12, A13, A22, alpha 1, alpha 2, alpha 3, and alpha 4. So here I realize that alpha 1 is equal to A11, alpha 2 A12, alpha 3 A13, and alpha 4 is this. These are the unknowns. What we actually know are these values. So this will imply that this implies that alpha 1 equals to A11, alpha 2 equals to A12, alpha 3 equals to A13, and alpha 4 is equal to A22. So that implies the following, that so here we have the following. So that means that so therefore A is equal to A11 E1 E11 plus A12 E12 plus A13 E2 yeah, let me see, A1, no, there is no A13 here. Is a mistake, as there is no A13 here. I wrote A13. Wait, yeah, wait a minute, that one, no, it's not A13, it's A21. Okay, A21, where is it again? A21, A21, A2 and 1. Okay, so here A11 E1 plus A12 E2 plus A21 E21 plus A22 E22. So in other words, if I take a matrix like that, any matrix that belongs to R2 by 2, suppose that entry is here, suppose that the entry is, let's say, 1 2 3 4. I can take that matrix 1 2 3 4 that I've created, and I can write it as a linear combination of this matrix E11 E12 E21 and E22. Okay, so it doesn't matter what I take, but any matrix that I can take from R2 by 2 can be written as a linear combination of these matrices that I have. So that implies that this implies that these so span, so these matrices E11 E12 E21 E22, actually they span R2 by 2. Okay, so I can write E11, I can write the following in a statement. So E11 thus E sub 11 E sub 12 E sub 21 and E sub 22 span R2 by 2. In other words, we can take any vector, any matrices from R2 by 2 and then write it as a linear combination of these. Okay, so conclusion now. Conclusion, because the conclusion, the first thing is the fact that E1 E11 E12 E21 and E22 are linearly independent matrices, are linearly independent. Second thing is the fact that E11 E12 E21 and E22 span the vector spaces where they have been, from which they belong to, span R2 by 2. Therefore E sub 11 E sub 12 E sub 21 and E sub 22 form a basis for R2 by 2, for R2 by 2. Right, so here we have shown that we have shown how to form a basis, and I would to show that some element of a vector space form a basis for that vector space. So question about this. Okay, so now let's continue. Okay, now here we here we have one, two, three, four elements, four items. But like if we wanted to use this theorem that is here, we need to have because here we're dealing with like R2 by 2. So here we need to have like if V is a vector space of dimension n. Okay, so we're looking at the here, for example, dimension of that vector space. That we're looking at the columns. Okay, so here like it's like 2. The dimension will be like 2. But like we cannot use that the theorem. We cannot apply it for that case. Okay, we cannot apply for that case, but I think the next case we're going to apply it. Here, for example, here we have dimension here is 3. It's a basis for R3. R3 is a set of all of the column vectors with 3 elements. Here we have like three vectors. Okay, dimension is equal to 3. We have 3 vectors. So here let's try to here show that these 3 vectors form a basis for R3. So according to let's read the theorem. The theorem here says what? If V is a vector space of dimension n, here we have a vector space of dimension 3 in the example that we have. If V is a vector space of dimension n, no set fewer than n vectors can span V. Okay, so there is no set that so you cannot find a vector you cannot find a set of vectors less than 3 that can span R3. That's the first thing. Second thing, any subset of fewer than n linearly independent vector can be extended to form a basis. No, I think no. This is not the theorem that I wanted to read. The theorem that I wanted to read is above. Here, this one. Yeah. If V is a vector space of dimension n, so in the example that we have, the dimension is 3 because we have R3. Okay, so if V is a vector space of dimension n is equal to 3, any set of n linearly independent vectors spans V. So if these 3 vectors, if I can show that these 3 vectors here are linearly independent, automatically it implies that they span V, they span R3. So I don't need to demonstrate that again. And vice versa, if you have those n vectors, remember the number here n has to match the dimension. If I have not 4, not 5, the same number of vectors as the dimension, so any 3 vectors, I'm going back to the exercise that I have, any 3 vectors that span V is linearly independent. So let me try to summarize again. V is a vector space, so we know that R3 is a vector space of dimension 3. Now if I can find any 2 linearly independent vectors in R3, those 2 linearly independent vectors will span R3, and at the same time if I can find 2 vectors that can span R3, it automatically implies that they are linearly independent. So here, if I can show that these 3 vectors are linearly independent, automatically it means that they span R3. And if they span R3 and they are at the same time linearly independent, they form a basis for R3. Okay, so the way I can easily solve this one is to calculate the determinant of this one. If I calculate the determinant, I find that the determinant is not equal to 0, and I have 3 vectors and dimension here is 3, then automatically they're forming a basis for R3. So let's do it. Alright, so here we have okay, so here we have show that these vectors that we have here, 1 2 3 and -2 1 0 1 0 1, this one is a basis for R3. So what I can do is, I know that the dimension of R3 is 3, because R3 is a set of all of the because it's a set of all of the column vector with 3 components. And I know, for example, in R3 I can have, for example, E11, E22, I can have these vectors, this one E1, E2, and then E3. I know that these vectors form a basis for R3, and the number of vectors that we have that form the dimension is the number of vectors in the basis. So here I know that the dimension of R3 is 3 based on just this one. I know that these are forming a basis for R3. Now I know that the dimension of the vector space that I have is 3, and I have 3 vectors. I have 3 vectors. So let us determine whether this one is are linearly independent. So I have the following. I will find the determinant of those. Let us find the determinant. Find the determinant of the matrix formed by these 3 vectors. So here I have 1 2 3 -2 1 0 1 0 1, and I have if I calculate that, I will have, so here 1 0 0 1, and here -2 here, and 2 0 3 1 plus 1 here, 2 1 3 0. If I calculate, I get 2. So 2 is not equal to 0. So those vectors 1 2 3 and -2 1 0 and 1 0 1 are linearly independent. And the vector space R3 has dimension 3, and we set one, 2, 3 transpose, -1, 0 transpose, and no, the vectors, not the set. The vectors 1 2 3 transpose, transpose, and the other one transpose are linearly independent. 3 linearly independent vectors by theorem 3, 4, 3. This set of vectors, now it's a set, now this set of vectors 1, 2, 3 transpose, negative 1, 1, 0 transpose, and 1, 0, 1 transpose span, this span of vectors spans our vector space R3. The vector space R3, and so that implies that because it spans the vector space, and it is so these vectors are linearly independent and they span the entire vector space, and as a result of that they're actually forming a basis. Okay, so by theorem this set of vectors spans R3, therefore these 1, 2, 3, so this set negative 2, 1, 0 and 1, 0, 1 is a basis for R3. Okay, so that's how for this one we can show that it is a basis for R3. So question about this? Okay, hold on. Okay, hold. Okay, so let's continue. Okay, so here I have okay, I have this for you. The first will finish, you post it on the group. I mean, you post it, the person will find the answer first as won the challenge. So x1 equals to 2, 1, x2 4, 3. The question is, does x1 x2 form a basis in R2? Now the amount, the winner, the first to find the answer will receive 150 francs CFA. So think about this, and I'm checking on the group to see who's finished first and who has the correct answer first. Alright.
Try something, sir.
You said?
I try something.
Okay, but you gotta post the result in the group.
Yes, I did.
Okay, let me see. Yes, your result is correct. What you've written is correct. I think this is your result, right? Let's see. Where is it? Okay, because of the light. Let me try this. Okay, it's not working. So yeah, but like definitely your result is right. So the amount of money was 150,000 francs CFA. But let me give the solution real quick. So here you have these two vectors. So to show that, so here we notice that we have x1 and x2. The question is, does x1 and x2 form a basis for R3? So we want to show that they are linearly independent first. Let's see if they are linearly independent. That's the first condition. So that means that I'm going to calculate the determinant of the matrix formed by these two vectors. So the determinant that I have will be 6 minus 4, which is equal to 2, which is not equal to 0. So that means that x1 and x2 are linearly independent. Now here R2, the dimension of R2, that's the first part. Now the second part, let's look at the dimension of R2 is our vector space is dimension is 2, and at the same time it is span we have two vectors, two linearly independent vectors. So here by theorem 3, 4, and 3, x1 and x2 span R2. Okay, and based on that we have, so here we have x1 and x2 are linearly independent. x1 and x2 span R2 as a conclusion. x1 and x2 form a basis in R2. Alright, so yes, so that's how we can justify that two vectors are forming a basis. So yes, so your answer is correct. Okay, so let me report that. Okay, so I think let me report that real quick. Here today you want this amount. Alright, so every time you do the, for example, for the homeworks, the price for that 250 francs CFA. Okay, now for some small, there are some small challenges that we have during the class called the J. So that's the J that we just done, and from that J she won 1500 francs CFA. Now let's continue. So we've done with the basis. Now there is something called change of basis. I'm going to skip it, and I'm going to go straight to row space and column space, because the part about change of basis is longer than the other part. That's why I want to do it in the end. It's longer than the other parts. Probably I can do it on Tuesday if God will, and if you are available. Okay, it's coming. So the concept of row space and column space is pretty simple. I can simplify this concept as follows. I have a matrix for example, I have a matrix A like this. With entries 1 0 0 0 1 0 like this. Now the set of all of the possible linear combination of the set of all of the possible linear combinations of the rows. This is a row, right? This is another row. So the set, let alpha and beta be scalars. So the set of all of the possible linear combination of this row and that row. So the set of all the possible linear combination. So alpha row 1, that is here, 1 0 0 plus beta multiplied by this row if I actually multiply, I'm going to have alpha 0 0 plus beta here 0 times 0, beta 0, and I can add the items alpha, beta, and 0 like this. So the set of all of the possible values that I can have from this, the set of all of the possible linear combinations of the rows of a matrix will form what we call it the row space of A. And the set of all of the possible linear combinations of the columns of the matrix A is called the column space of A. So suppose that I have so the same matrix A here, and I suppose that I have alpha, beta, and gamma be scalars. Okay, scalars. By the way, I can even leave that row space like this. I can leave it like this. Okay, I can write something like this, like alpha 1 0 0 like this, plus beta 0 1 0. I can leave it like this. Okay. Now let's look at this is the row space of A, and we also have the column space of A. The column space of A, that's all of them be scalars like this. So I take this column that is here. So this column here. So it's like the set of all of the possible linear combination of the column of your matrix. As simple as that. So alpha, the first column, plus beta, the second column, plus gamma, the third column. And if I multiply the alpha here and beta here and I add in everything, I get the following: alpha and beta. So the set of all of the possible linear combinations of the columns of my matrix A will represent my the column space of A. Okay, so that's the concept in a nutshell. So now let's talk more about this. With the notes. So row space and column space. See, hold on. Okay, hold on 1 second. Hold on 1 second, it's coming. So here, row space and column space. If A is a m by n matrix, the vector m, the m vectors corresponding to the row of A. So here you have a matrix. M represent the number of rows, n represent the number of columns. So the m vectors corresponding to the rows of A will be referred to as the row vectors of A. Similarly, each column of A can be considered as a vector in Rm, and we can associate n column vectors with the matrix A. Definition: if A is a m by n matrix, the subspace of R1 by n, meaning that you are looking at this one here is row, so one row n column, right? So it's like you're taking a vector, you're taking the row as a vector, so you're looking at the rows, right? So if A is a m by n matrix, the subspace of Rn spanned by the row vectors of A is called the row space of A. Now the subspace of Rm spanned by the columns of a matrix A is called the column space of A. In other words, here Rm is like the linear combination of the columns of A. To make it simple, this one, the row space, is the linear combinations of the rows of A. Example: let A being this matrix, give an expression in terms of vectors of the row space and the column space of A. So let's do it. I actually did it already, but let's do it in a more formal setting. So here I'm going to write the following. Let A be the matrix that I have. Let A being the matrix 1 0 0 1 0 0. Now here let alpha and beta be real numbers. So here here I have alpha, the set, the row space of A, the row space of A is the set of all linear combination of the rows of A. So it is given by the following: alpha 1 0 0 plus beta. So you take alpha, multiply it by the vector that you can form with this row, plus beta 0 1 0, and that is equal to alpha beta 0. The next one, the column space of A. The column space of A is the set of all vectors is the set of all vectors of the form alpha first column, alpha the first column plus beta the second column plus gamma the third column, and that is equal to alpha beta, like this. So here we can see that the row space of A, the row space of A is a two-dimensional subspace. So the row space of A, the row space of A is a two-dimensional subspace. What do we say two-dimensional subspace? When we say, remember, the subspace is like so let me rewrite. I said that I can write it in terms of a set, right? Because this represents the set of all of the linear combination of the rows, like this. So it's like normally in set notation I have like a brace like this: alpha 1 0 0 plus beta 0 1 0, like this, such that alpha belongs to R and beta belongs to R. Okay, that's like the set notation. In set notation, this is like the set of all of the linear combinations of the rows of A. Now why do we say that is two-dimensional? Because we have two vectors. Okay, here we have two vectors, so the row space of A is two-dimensional. Okay, it's two-dimensional. is a two-dimensional subspace of R1/3. So here is the set of all of the, so R1/3 is your set of all row vectors with three with three elements, with three items, or three components, okay. So the row space of A is a two-dimensional subspace of R1/3, and the column space of A is R2. Here you see that we can write it as a linear combinations of vectors from R2, as you can see. Okay, alpha, one vector from R2. This is like actually E1, that is here. E2 here is like simply 0. So we can see that we can summarize this one as E1, E2. So here we can see that it's a linear combinations of the two elementary vectors in R2. So we can say that the column space of A is R2. Now let's go to our goal in here. Wasn't to talk, it was actually to write this in that. That was our goal in this section. Now the next one, so that example number 1 has been done. Theorem 361. Two row equivalent matrices have the same row space. So if you have one matrix, you determine its row space, and you have another matrix, you found its rows. You have two matrices, and then those two matrices are row equivalent. That means that they have the same row space. Okay. Definition: the rank of a matrix A, denoted by rank of A, is the dimension of the row space of A. Okay, the dimension of your row space of A is your rank. Okay. Now to determine the rank of a matrix, we can reduce the matrix to row echelon form. The non-zero rows of the row echelon matrix will form the basis for your row space. So here remember that the non-zero rows, the rows that are non-zero, not column here, but rows that are non-zero, form a basis for your row space. So you take a matrix, if you want to determine its rank, you reduce, you do row echelon form. Once it is in row echelon form, then you can determine you can determine its rank. The number of non-zero rows will form a basis for that. So let's do the following example. Given a matrix, find its row space and its rank. Okay, so let's do this one. Okay. So we have the matrix A here, that is like this. Two, -5, -4, 3, 1, -7. Okay, now I suppose that we all know how to do. We know how to find row echelon form. So we reduce by reducing the following matrix by doing by performing row echelon form, performing a reduction on the matrix A. By performing the reduction on the matrix A, we have the following row echelon form. So we have the following matrix: 1, 0, 0, -2, 1, 0, 0 in here, 5 and 3. So here, so let's call this matrix U. Let's denote it as U. So as you can see, for row space you are interested in the rows, and we are interested specifically in non-zero rows. Now here clearly, so 1, -2 and 3 and 0, 1, 5 form a basis for the row space of U. But remember, in we know that by theorem, the previous theorem, by theorem 361, two row equivalent matrices have the same row space. So that means we know that A is row equivalent to U. Okay, by theorem 2.1, two row equivalent matrices have the same row space. Okay, thus U and A have the same row space. And we know that the row space of how do we call that? The dimension, we know the row space is formed with two vectors, right? The row space of A is formed by two vectors, 1, -2, 3 and 0, 1, 5. This means that the dimension of the row space of A is 2. Okay, so the dimension is the number of vectors that is formed by your for like the number of vectors in your basis basically. So here these two vectors, they are forming the basis for the row space. So that means that they actually, the number, the dimension for that row space is actually 2. Now we said that the rank is equal to the dimension of the row space. So here that implies that the rank of A is 2. Okay. So here we have answered the question that we were asked. We are asked to find the how do we call that, the row space of A, and also to find the its rank, and that's what we have done in this example. So any question related to that, so what we can do, we're going to finish it, if God will, on Tuesday. All right, we're going to stop it. We're going to stop here today. So questions related to this, and I'm going to send you homeworks. I'm going to send you homeworks as well for Tuesday related to what we have seen today. All right.
Okay, sir.
Mm-hmm. And I think I haven't sent. Did I send you the section on the row space? Did I send it to you? The section on the row
Could you
space.
repeat, please?
Did I
Section
the
16.
no, the lecture notes on row space? Have you received it, or you have not? Not yet. Okay. So I'll send it to
I
you.
saw this in the book.
I'll send it. I'll send it again.
Okay, sir.
Mm-hmm. All right.